Okay. I think it's time to start. So let's see if everything okay here. This looks fine, and let me try test the pen a little bit here. And okay, I think we are good. Yeah. So welcome to the first class of our Introduction to Quantum Computing course. Yeah, this is a course I open every year for Introduction to Quantum Computing, also for all the students, my first year grade students and all other students, to get into some background of doing quantum computing research, or you just want to learn quantum computing. And today, well, it's the first day of class, and so we are going to do the usual course introduction, and if we have time, we're going to delve into the mathematical background of quantum computing first, because quantum computing is a course about incorporating quantum mechanics into computing. So it's a hybrid between quantum mechanics, physics, and computer science. And since I assume most of us here are having CS background, so I will spend more time on talking about. So the first few weeks into talking about quantum mechanics. So we don't assume physics background here, because I will teach you about the relevant physics. And but we also are using some physics math notations. So we'll start with doing the linear algebra in physicist way. Okay. And first, this is course information, and we use this textbook, Quantum Computation and Quantum Information. This is a quite standard book by Han-Hsuan and Chang. And yeah, we don't quite have the cover here, but yeah, it's a famous book. You can Google its name. And the course structure is mostly followed by Han-Hsuan and Chang, but also there are some addition and rearrangement by me. And we don't actually cover the whole book. We only go through the first half, which is more about the algorithm part. But the later part is also very interesting. We will have more information theory and and error correcting stuff. Okay. And we have a course website. It's just the NTHU website on eLearn, and a lot of things will be posted here. And most importantly, homeworks will be posted here. And I think also upgrade the homework to eLearn. And we also post lecture notes on eLearn, and I already post the lecture notes from previous years, and also we have recordings every year, almost every year, and the past recordings, the links are also here. Okay, and about the videos, so we will be streaming our lectures every class on this YouTube channel. And yeah, so you can just click it, and it's just a YouTube channel of my name. So all my courses are basically streamed here. So if you miss a class, you can watch this online, or you can even check the past videos for the class. And yeah, so we don't take attendance, but if you don't come here, then you lose the chance of asking questions. And yeah, yeah, but yeah. You can use the way that you think is best to learn the materials. And the instructor is me, and my office is just the 6th floor of this building at 610. And this is my email, so you can, if you have some question, you can email me. But I think most of the question will be handled by our hardworking TA here. So the TA Li Weichen, maybe stand up a little bit so you can see. So TA will handle most of the stuff, hopefully answer your questions. And anyway, he will be responsible for collecting and grading the homework. So yeah, and his office is the 4.444, so it's in the next building there. And this is his email address. Okay. And so that's the general information. Any questions so far? Okay, and then we have the schedule of that class. And so first half, is more on background. So we start with talking about this Dirac notation and of course quantum state, quantum measurement, and then general basic quantum mechanics and quantum information. This is about 2 to 3 weeks, and then we start teaching about Then we start our quantum computation. We talk about what is a quantum circuit, and we also talk about a bit of a complexity theory. So what are all those big letter complexity classes are? And so there are the famous P and NP. For most CS background people, we probably learn those, but we'll talk about the quantum part with BQP and QMA. And so those are basics about quantum circuits. And then next we'll talk about simple quantum algorithms. So this George algorithm and Simon's algorithm is where people start to realize quantum algorithm can have some speed up. Then we have our midterm. So for now we say it's on week 8 because we are 16-week schedule. And then on the later part of the course, we'll teach you about the 2 most famous quantum algorithms. So it's the Shor's factoring algorithm and the Grover search algorithm. Okay? And but each of them are very nice algorithms, so you have a lot of relative theory, a lot of series related to them. So for example, for Shor's algorithm, you also learn about quantum Fourier transform and phase estimation. And in Grover algorithm, you will learn about the Oracle model and some way to lower bound your query complexity. But actually, Oracle model will learn a little bit the Simon's algorithm and the George algorithm already. Okay. And anyway, so finals will on week 16. Okay. And finally, this is probably people care a little more about. So it's about grading and the homework policy. And the grade will mostly be on the exams. So exam will be the midterm and the final will cover for 60% of the grades, and the homeworks will be 30%. And the homework policy will have a lot of homework. So homework will be out we'll basically have homework every week except around the exams. Okay. And so homework will be out and due on every Thursday, including this Thursday. So this Thursday we'll hand out the first homework set. And I guess the training class is kind of changed, right? So it used to be training class, but I think it's more like upload to either, depending on how Western like. Yeah. Yeah. So I guess that's. I guess the training class is also okay, but let's add a little bit here. So yeah, we find out that upload to e-learn is also good. Upload to e-learn. E-learn. And in general, we don't want late homework because handling late homework is quite tedious for RTA. So yeah, in general, late homework unless you have very good reason. Okay. And but to to compensate for we not taking late homework, we'll let you slack over one time. So the lowest score homework will not count toward final grade. So you can just skip one homework if you really have trouble finishing it. Okay. And I guess any question again? I think that's most of the organization stuff. And next slide is just we have some nice online lecture notes you can also check. So those are quantum computing classes by other accomplished computer scientists. So we have the Skyler's lecture notes here, and the Ronald D. Wolf lecture notes here, and the Andrew Charles lecture notes here. And they all have different flavors, and you can check. So if you want something extra, then you can see how the quantum computing classes are taught in other schools. Okay, and but they are all in English also. Okay. So I think that's the organization stuff. If people don't have questions, then let's start getting into the actual class. So the scope of this file, so this is our first file, and it's about introduction, a short introduction to quantum computing. Then we'll start to teach you about linear algebra. And as a small notice here, so we don't do a whole review of linear algebra. So if you have questions, you can check them from other sources, or you can ask me or the TA, Wei Chen. Okay. And yeah, so start with quantum mechanics. So very high level, what is quantum principle? So quantum mechanics is really a principle, although it's physics, but it's really about information. So quantum mechanics, to me, it really says that information in the universe is stored in a way that, so it's really about information. So it's stored in a way that's quite unintuitive to us. So when in our usual classical information, you just think information is just something written here, you can read, right? So like this slide here, you have a lot of information here, and everyone can read the information and nothing happens. Okay? But quantum information is really weird. Okay, so it has this. I think it's weird in these two principles. So the quantum information is really superposition of classical information, and for now superposition. So this thing has a very mathematical, rigorous definition. But for now, it's kind of like a probability mixture, but where the probabilities are complex numbers. Okay. And then there is a measurement, and so we kind of think quantum information is something weird, and it's in this weird superposition state. And then if you actually want to learn classical information out of your quantum information, then you need to do measurement, and something weird will happen. So we kind of have this worldview that we have quantum stuff storing quantum information in some weird way that you can manipulate in weird way. And so there is this vague boundary here. So it says this side is quantum stuff, and this side is our familiar classical world. And we will do some measurement to learn to get your quantum information out of your quantum world and learn it as a classical information to classical server. So probably you. Okay. And so this is our very easy interpretation of quantum mechanics. And to digress a little bit. And this is where a lot of physicists will start arguing, or even or more like a philosopher will start arguing, because the question is, why do we have this line here? Okay. So a lot of I guess the foundations about quantum mechanics is asking about this line. Okay. So, because physicists usually believe that their theories works for everything. So, for physicists, they believe that quantum mechanics is the base law of the universe. So they think everything should be in quantum mechanics. So they think that this line should exist and everything should be quantum. And then you will get a lot of trouble in interpretation about what does it mean by myself having a superposition with myself, etc. Okay, and so that's where a lot of the philosophical question will happen. And in general, the question is about why can you cut this line here? So the whole universe should be in quantum. And but anyway, there are some ways and evidence to argue that this line really happened. And I guess this also works with our experimental experience. Experimental experience. So in general, it's quite easy to. So if you're working in a lab, it's quite easy to see that some of the stuff is quantum and other stuff is classical. And so we just adopt this worldview, although we have this weird line here. But we adopt this worldview and it works in our course. Okay? So we have some quantum stuff that will be in quantum in the quantum rules, and we'll do measurement and we'll do some control to interact with the quantum stuff. Okay. So there are also something, I guess. So there are also some control you can do. You can do classical control on quantum stuff. Okay. So this is our worldview of quantum mechanics, and then I'll talk to a little more about the quantum principles. Okay. So as we say, quantum state can be in superposition, and for example, a very famous example is a qubit. So a classical bit is either 0 or 1. It's basically the smallest amount of information you can store. It's a bit. It's a 0 or 1. And a qubit is a superposition, can be any arbitrary superposition between 0 and 1. Okay? So we write it as this. So we say qubit is in this state k psi, and then we'll talk about this notation soon later. And the k psi is some alpha of this 0 of this 0 state plus some beta of this 1 state. And alpha and beta are complex numbers. They are called amplitude. And 0 and 1 is is like a classical 0 and a classical 1. Okay? And yeah, so this is what we believe in quantum mechanics. So your state you always in some linear space, and there can be some arbitrary linear superposition. And where the classical states are usually also no basis of your linear space. So this is 0 and 1 here. And then when you do measurement, then something weird happens. When you do measurement, you start with your superposition state, and when you do measurement, then the state collapses into classical state. And this is really something don't happen in classical formation, because measurement, as we say, measurement is where you read the information out of your system. But classically, you read the information, and the information is still here. Like the slides are here, and each one of you reading it doesn't change the slides, that they are still here. But quantum system is really weird. You read the system, and the system will actually change. So the quantum system will actually collapse into classical states, and with some probability. Okay. So for example, we have this state with amplitude alpha 0 and beta 1, and when you try to read the state, we say we do a measurement on it, and then will collapse into either 0 or 1. So it will become a classical state. Now it will read like a classical state out, and so it has alpha squared probability to become 0, and the beta squared probability to being 1. Okay, and it go into 0 and 1, and the observer will learn it's 0 and 1. But state will just become 0 and 1, and it's never this alpha 0 plus beta 1 again. Okay, and then now the question is, what does the quantum principles mean? Okay, and by what I just described, this superposition looks really like just a probability distribution. It's like you flip a coin, and you have the probability alpha squared being 0 being head, and probability beta squared being 1. Okay, so you might ask, is the superposition is just classical randomness? It's like you flip a coin or a roll of dice, and you cover it up, you don't know what it is, and it looks like a superposition. So is the superposition just classical randomness, but you change it to a fancy name? And but on the other hand, people are also saying that the superposition allows you to do exponential parallel computation. You say that you can use this superposition into different branches, and it will give you exponential parallel computation. Okay? Those questions to these are answers to what are the answers to these questions, and it's what we'll find out in this class. Okay. And okay, so that's a very short intro to quantum mechanics. And let's go to the dirty work. Let's go back to linear algebra. So now we go back to total limits. Okay. And the first thing about linear algebra, okay, so this might be a little different from the linear algebra you learn in in undergrad. It's because we work with complex number or complex scalars. So numbers here are complex. Okay. And here we review a little bit of linear algebra concept. So we know there are vector spaces, and the vector spaces has subspaces, and different vectors can have a linear dependency span, and a vector space has a basis, and the number of basis element is a dimension. So I guess a very quick review of basis. Set of vectors that span your vector space, and there are color and row space. Okay, and more important concept we'll use a lot is the eigenvalues and eigenvectors. Okay, So there are eigenvalues and eigenvector to our matrices. And for vectors, there are three different products we'll talk about. So there are inner product, which is a scalar, and there are outer product, which is a matrix, and there is tensor product. So tensor product is a weird object that you probably didn't learn in your previous linear algebra course, but it's a very important concept for quantum computing, and this will spend some time to talk about at the end of this slide. Okay, and there are also property of matrices, and actually a little more, but three of them that are quite important are Hermitian matrices and PSD matrix, or PASD matrix, positive semi-definite, or positive definite matrix, and there are unitary matrices, which is also just which is orthogonal matrices if the matrix elements are real. Okay, and so let's first go into this weird notation. So we were writing this weird K notation in our quantum information intro, and this is called a Dirac notation. Okay. So those are basically linear algebra notations for physicists. And because of the physics background in quantum computing, this is also a standard notation of linear algebra in quantum computing. Okay. So we will write symbols like this. So this cat symbol, so it's a straight line with angle here, and it's a called cat, and you can have different symbol inside. So for example, we have psi cat and phi cat here, and this notation really just means column vectors. So for example, we have psi cat here, and it's a two-dimensional vector 1, 2, and then we also have this bra notation. Okay, so it's just an angle and a straight line. And so we have this psi bra and the phi bra here, and they are really just row vectors. So we have, for example, we have phi bra here being 3, 4. Okay, so it's a two-dimensional row vector, and we will use capital letters as matrices. So we have A, B, C, etc. They're just matrices. So we have big A, so this is 2 by 2 matrices. Sorry, 2 by 2 matrix. So 1, 2, 3, 4. And then we have weird notation now. Okay, so we can have our matrix multiplication in this notation. So we can have a row vector multiplying a matrix, then multiply this row vector multiply a matrix multiply a column vector like this. And then we start. Okay, and so we have this row vector phi, then multiply our matrix, then multiply our column vector, and then you just do usual matrix multiplication. So row vector multiply a matrix multiply a column vector, and then you do this multiplication, then you find out the answer is 59. Okay, and but the next thing to notice here is that okay, so things are I guess I should say here is a bit funny, but usually when we just write a bigger matrix here, so they are usually square matrices. Okay, excuse me, square matrices. I think there are very few exceptions. So if you just write the matrices, they are usually square. Means that the dimension of a row and a column is the same. Okay. Square matrices. Okay. Okay, so usually the matrices are square, and when you write this notation, dimension of psi will equal to dimension of phi. I guess it doesn't matter. Yeah. But anyway, so when you write this notation, then you find out that you have a row vector multiplied by matrix multiplied by column vector, and what you get is a scalar out. Okay. And also, small anecdote. So why do we call this bra and a cat? Because we think this is a bracket notation. So if you have this whole thing together, you see you have this left side angle here and the right side angle here, and together is a bracket. Although the spelling is a little wrong, so it should have a C here. But yeah, so together is a bracket. And one thing to notice is that so a good I guess a good sanity check when you do computation is that when you multiply something together and you see they form a bracket, then it should become a number. Okay, so let's write here. A bracket give you a number. A bracket is a number. Okay, so that's a good sanity check when you do computation. This looks very simple here, but it will get complicated when we talk about tensor products. Okay. Okay, so for just right now, really nothing extra happened. Is we just excuse me, we are just writing column vector, row vector, and matrices in different notation. Okay, and okay, and I guess I want one more example here. Okay. And one more example, and something lazy will do is so we can also have just a row vector multiply a column vector, right? So we can have this bra phi times ket psi. Okay. Oh, sorry. So if we write down, usually it's like this. So this bra vector times the ket vector, and but usually will be lazy, and so we won't actually write double line here, so we just write one line in the middle. So that's a standard notation. Okay, what I want to say, and then you can do the multiplication. Once again, you see it's a bracket and it's just a number, so it's 1 times 3 plus 2 times 4, and it's just 11 here. Okay, so that's a bracket notation. And then next we have something we can do to matrices. Okay. And there are 3 operations we can do to complex matrices, or 3 transformations. Okay? And the first one is complex conjugation. It means that you just put complex conjugation on every element of A. So you see if our A equal to 1, 2i, 1 minus I, and you do complex conjugation, then 1 and 2 just stay 1 and 2, then I become minus I, and 1 minus I become 1 plus I. Okay? And the second one is something you should learn in linear algebra course. That's the transpose of the matrix, and it just means you flip around the diagonal. So the diagonal elements stay the same, so 1 and 1 minus I stay the same, and 2 flip to the symmetric position, so 2 flip to here, and I flip to here. Okay, so it is the transpose of your matrices, and actually. What we'll do most in our course is a dagger operation. Okay. So it's A to this weird dagger symbol that's very hard to type in PowerPoint. Okay. And so dagger is really just a complex conjugation plus transpose. So you do both on your matrix, and we call it dagger. And if you want to be more fancy in mathematics, it's called the adjoining operation. Okay. Okay. So the dagger operation on matrix A is really you do transpose and then you do complex conjugation, or you can do complex conjugation and then transpose. It's the same. Okay, and yeah, so let's write it here. So A dagger is you do transpose first, then you do adjoin. So it's 1, 2, then I become minus I, and 1 minus I become 1 plus I. So A dagger equal to A transpose star equal to A star transpose. Okay, and okay, and as you said, the dagger operation is very important because we'll see very soon. It's really related to inner product, and we define another notation related to dagger operation. That is, if you have some vector. Some column vector psi, and we define its corresponding row operator as a dagger. Okay, so for example, you have so yeah, so if we have already a k psi defined, then we also have bra psi defined. That's as the dagger of k psi. So if, for example, if our k psi equal to is 1I vector, then we have our broad psi equal to U transpose, so it becomes a row vector, and so it's 1 and something. So it should become I, but you also do complex conjugation, so this I become minus I. So we define broad psi as the dagger or conjugate transpose of our K operator, and also also the other way is also defined. So if you have okay. Yeah. So it's basically we see this dagger as so it's basically we view this column vector as a matrix, and say we complex we transpose conjugate this matrix, and then it become a matrix with this row dimension 1, column dimension 2. Okay, and you can obviously check that a dagger will equal to A. Okay, and the other thing you can check is that you have two matrices multiplying together, then AB dagger will become B dagger times A dagger. Okay, any questions so far? Okay, and then let's go to some more computation. Now let's talk about inner product. Okay, so the inner product inner product is now the complex inner product. Okay, and we'll define complex inner product in this very mathematical way, and we say that the inner product between two complex column vector is you do you do adjoin on the first vector, so you turn V to V adjoin, then multiplying that with W. Okay, and so we write this as this. So this adjoint become V broad, so it's written as this V broad times this W. And as we said, we skip our HR line here, and we just write this V straight line W here. Okay, so that's the inner product between the two column vector V and W, and this will have several properties. So this inner product will be linear in second argument, means that you have a linear combination of your second argument. Then the resulting inner product is the linear combination of the inner product of this separate Wi. And the inner product is not quite symmetric in its two argument. It's now because it's complex. Okay. So for real number inner product, then V inner product with W equal to W inner product with V. But if V and W are complex vectors, then the inner product, then you switch order, then you actually get the HR complex conjugation. It's because it's dagger here. Okay, and the other property of inner product is that the inner product of a vector itself is 0 if only if the vector is 0. Okay, but anyway, let's see example of inner product. So you have a ket psi equal to this 1 minus I vector, and the ket phi equal to this minus 1 minus I vector. The inner product between psi and phi, as say, is the adjoint of phi. So it is 1 I vector. You become I because you need to do complex conjugation, and multiplying with your psi vector. So it's 1 minus I. And they actually do a calculation, then you see that it's minus 1 and plus 1, and so it becomes 0. Okay, so this is complex inner product. It's a little different because the first vector you need to do complex conjugation to its coefficients. Okay, and then we kind of see so we kind of see why we want to have the complex conjugation, because you think about we want to have our complex inner product to define a norm of our vector. So we define a norm of our vector V as the square root of its inner product, and then you think about V being some complex vector with A and B. Oh, so sorry, I have a little typo here. Then the norm of V will become yeah. So the norm of V will become absolute value of A squared times absolute value of B squared. Okay. And for two vectors, we can define whether they are orthogonal to each other by checking their inner product. This is a geometry induced by this inner product, just like as in real number. Okay, so we say two vectors are orthogonal if only if their inner product is 0. Okay, and so we have a norm of our vector defined here is the square root of its inner product, and we say a vector is normalized if its norm is 1. So meaning that it's also called a unit vector if its norm is 1. And then we have other concept. So we have a lot of vectors. So so if we have a set of vector, then we say the set is orthonormal. If every vector is a unit vector, means that their norm is 1, and also the vectors are all orthogonal to each other. Okay, and then we have this concept of orthonormal basis. That just means the basis that is orthonormal, means that all the basis element with norm 1 and all the elements are orthogonal to each other. Okay, and so it's a very strong restriction on the basis, but also from linear algebra course, we know that we will have just any basis, then we can apply grand strip procedure to get the orthonormal basis. Okay. Okay. Any questions so far? Okay. If not, then let's go to outer product. So outer product is written as this W and V. Okay. And once again, you can kind of like inner product, you can just think W as a matrix and V as a matrix, and just think of this as a matrix multiplication, and you will get a matrix out of this. Okay, and you can also think of this as a linear operation. So if V is a vector in space V, and W is a vector in space W, then WV will be a matrix that map from V to W. And for example, if you have the psi vector, k psi vector as 1 minus psi, and k phi vector as minus 1 minus psi, then we can write this outer product as just psi ket and phi ket and psi bra. And psi bra once again is the is the conjugate transpose of this psi ket. So it's a minus 1 and the minus I become I. Okay. And the outer product with our notation is just these two matrices multiplied together, and then you see that it becomes a 2 by 2 matrix, because the first row is 1 times its minus 1i, and the second row is its minus I times its minus 1i. Okay. And okay. And I think we have about 10 minutes. And then we go to this eigenvalue and eigenvectors. Okay, and we only define them for square matrix. So the A be some n by n square matrix. Okay, and eigenvector of A is a non-zero vector, such that if you apply A on the vector, then you become a scalar multiple of your original vector. Okay, and this scalar multiple V here is called eigenvalue of A correspond to V. Okay, and yeah, so I guess this equation is the most important here. We have AV equal to VV. These are eigenvectors. Okay, and now here is a small review of how you find eigenvalue and eigenvector. That is, you can first find eigenvalues of a matrix by using the characteristic function. So you can find C of lambda equal to determinant of A minus lambda, and so I guess it's called characteristic function or characteristic polynomial. Okay, characteristic polynomial, and the eigenvalues are the characteristic polynomial. And the eigenvalues of A are the roots of the characteristic polynomial. Okay, and Okay. And yeah, so as we said, so we have our matrix A here, A equal to this 2i and 3 and minus i2. Okay. And we also have this notation of null of some matrix, meaning n of some matrix B means null space of B. And as we say, we want to solve the characteristic polynomial. We find its root. Okay. Find the roots of the characteristic polynomial, and it means we want to solve delta, the determinant A minus lambda I equals 0. So we have A minus lambda I, where, okay, we didn't say. So we should say here, so I is identity matrix. Okay. Wait, excuse me. I didn't. Excuse me. Excuse me. So I equal to identity matrix. Okay, and yeah, so as we see, minus lambda I just give you minus lambda on the diagonal because I is the identity matrix. And so if you solve this equation, you will see that if you want this to be 0, then lambda equal to 3 or 1. Okay, and for lambda equals 3 to 1, then then you want to find the eigenvalue corresponding to lambda equal to 3 or 1, then you want to find the null space of A minus lambda I. Okay, so for lambda equal to 3, you want to find the null space of A minus 3 times identity, and that's the null space of this matrix minus 1 I minus 1. Okay, and yeah, so we find out this two-dimensional space is spanned by this 1 0 I and 0 1 0. And for lambda equal to 1, then you want to find the null space of this matrix 1 0 1 0 2 0 and minus I 0 1. And you see that it's spanned by this only one vector 1 0 minus 1 minus I. Okay, and so you see that for lambda equals 3, we have two eigenvectors 1 0 I and 0 1 0. And for lambda equal to 1, we have the eigenvector 1 0 minus I. And we also like to normalize our eigenvectors, so we also have a square root, one with square root here and one with square root here. And so up to now is a review of how to find eigenvalue and eigenvectors of a matrix. And here we have another concept here that's called degeneracy. That's you probably learn in linear algebra, but it's very important here. Okay. So maybe I should highlight it here. Okay. As you will see later, this is quite important in quantum mechanics. So the degeneracy idea, mathematically, is very easy. It's just that some eigenvalue has more than one eigenvectors. So for example, you have eigenvalue 3 here, and you see that it has two linearly independent eigenvectors. So it has this 1 0 I and 0 1 0. Okay, and yeah, so this is what we call degeneracy, and yeah, we'll call these two. This I will call this eigenvalue 3 and those two eigenvectors degenerate. Okay, and yeah, this is something we'll investigate more in next class. And I think we have 5 more minutes. It's a little annoying. Okay, I guess we can go through this and take a break. So very quick review next time. Okay, and I guess a question for now. Okay, anyone question for finding eigenvalue and eigenvectors? Not. And then we go to talking about property of matrices. Okay. And there are some property of matrices that we'll use quite often in this class. So right now it's kind of just names. So first is Hermitian. We'll call a matrix Hermitian if A dagger equal to A. So remember, dagger is a is a transpose conjugate. Okay. So if a matrix equal to its transpose conjugate, then it's called a Hermitian. And you can prove that if A dagger equal to A, then all its eigenvalues are real. And then there are positive definite matrices, and that means that basically all the eigenvalues of A is greater than 0. But if we want to write a definition, we can write it in this way. So it means that if you kind of sandwich A between any vector, so you have this psi bra times A times psi ket for every psi that's not 0, and if this is greater than 0 for all psi, then we call A being positive definite. And you can kind of see it from this here, because positive definite A will have always eigenvalue greater than 0. And similarly, you have positive semi-definite, such as psi ket A psi, and it's greater or equal to 0 here, and you have eigenvalue greater or equal to 0. And another matrices, set of matrices are very important, are the unitary matrices. And the matrices that with A dagger A equal to identity. Okay. And if you write A in eigenvalue decomposition, it will give you that all the eigenvalues of A equal to 1. Okay. And yeah, also here we have other properties that we'll talk about later. Okay. And okay, and unitary matrices. Okay, and I think I will end here, but let's just be really quick. Okay, and as we said, unitary matrices are very nice because they are going to be transformations of our quantum states. So transformations of quantum states are all going to be unitary matrices, and that's because unitary matrices has this nice property that they preserve inverse product. That means that you have some fixed unitary matrix U here, and you apply it on ket psi and ket phi, and then you'll find out that this inner product will equal to the inner product with just ket psi and ket phi. Because if you write down the definition of inner product here, is a uk psi and the uk phi, it becomes this you need to calculate it by having the adjoint of uk psi, and which equal to adjoint of k psi means bra psi, and adjoint of u being u dagger, and so it's k psi, u dagger, u, and ket phi. And then we use the fact that matrix multiplication, you can resolve them in any order. So we can do the matrix multiplication of these two matrices first. Okay, so this is u dagger u, and then we know that u dagger u equal to identity, and so that's just k psi times k phi, and so that's just bra psi times bra times ket phi, and that's a definition of inner product between ket psi and ket phi. Okay, and also I guess a nice property of the unitary matrix is that if U is unitary, then we have the, so we say that U dagger U equal to identity, but U dagger is also equal to identity. Okay, I think that's time for our class now, and the people have any question? Otherwise, I will see you on Thursday. Okay, yeah, so see you on Thursday. 啊？什么？作业怎样？
的档案那些。
作业档案我没有把它放上去嘛，对啊。我再 share 给你。
好。然后那个依赖上面，
依赖上面，对，我剪，我们现在就夹好了。 加一下。先跟同学讲怎样？
我是想
要加签吗？加签基本上都可以，就是你送表单就可以了。
好，
对对对。
好。那我还有另外一个问题是，就是考试跟作业的形式都是
什么意思？
就是
作业考试的话会现场考试，考试会有一部分跟作业一样嘛，就是会有比较简单的部分，比较难的部分。简单大概是60分这样，然后会有中间，然后比较难。但考试有时候我会觉得我出比较难，就给你们超过100分这样，看看状况的，这样。
然后就是都 coding， 就是全部都是 coding，
就是通常其实都比较数学部分，会是一些数学计算问题。考试都是考试的作业都是手写的，
都是手写的。
对，大部分都是手写。
是这样。
就是12点接触量计算来说，
对啊，我的希望是这样的，没有接触过这个。
都是在算数学吧？都是在算
大部分在算数学。
那考试的话是只有期中跟期末还是？
对，只有期中跟期末。
那作业的话大概有几次啊？
作业会有13，现在可能比较多，可能会有12次左右吗？
就基本每个礼拜都有作业。
对啊，每个礼拜都有作业。对啊，每个礼拜都有作业。
那作业会大概有几题类的多吗？
几题哦？我是觉得不多啦，没有。4、5题吧。
所以就是那个作业跟上课会教吗？还是
作业题目应该上课都会教。
然后考试跟作业有关。
考试会跟作业有关，但当然也是有的，在作业里面没有题目这样子。
都是手写嘛？
对，都是手写。
手写。
那个招牌真的。